All right, we're starting chapter 5, and we're going to start with some fundamental trig identities. So the purpose of this chapter is to use some of these trig identities that we're going to learn, and we're going to memorize, because we're not given any formulas or anything for the AP test. We're going to be performing substitutions, simplifying expressions. We're practicing that skill so that we can solve trig equations and inequalities that may require some of these substitutions. So back in chapter 4, we learned about 6 trig functions, and we know which pairs are reciprocals of each other. So these are the first identities. They're called reciprocal identities that you need to use. You won't need to be able to name the identities, like you don't have to know that these are called reciprocal identities. You just have to be able to use them. So we know that sine and cosecant go together. So one identity is that the sine of theta is equal to 1 over the cosecant of theta. And then the reverse of that is true as well. The cosecant of theta is equal to 1 over the sine of theta. And we know that cosine and secant go together. So the second pair of reciprocal identities is that the cosine of theta is equal to 1 over the secant of theta. And the secant of theta is equal to 1 over the cosine of theta. And then the last pair is tangent and cotangent. So the tangent of theta is equal to 1 over the cotangent of theta. And the cotangent of theta is equal to 1 over the tangent of theta. So those are reciprocal identities that we will use as we're trying to simplify expressions. So we're just getting some of these rules down first. Also in chapter 4, we worked a lot with the unit circle, right? The unit circle was a circle with a center 0, 0, a radius 1, and this point on the ordered pair, this xy coordinate, can be calculated using trig, assuming that this angle from the x-axis to the terminal side is theta. So what do we know about this unit circle? Well, the x-coordinate is the cosine of theta, because we're in the unit circle. And the y-coordinate is the sine of theta. And using our unit circle trig, we know that the tangent of theta is the y-coordinate divided by the x-coordinate at any point on the circle. And now we can make some substitutions right here. Because y is equal to sine theta and x is equal to cosine theta, we can also say that the tangent of theta is equal to sine theta over cosine theta. That's actually our first quotient identity. The tangent of theta is equal to sine theta divided by cosine theta. So again, that's one to memorize, but you already know that tangent is y over x. So if you can keep that substitution or connection to the unit circle, it's sort of already memorized. You're just writing it in a different form. Okay, also the cotangent of theta, we know that on the unit circle, that's the x-coordinate divided by the y-coordinate at any theta. And because we know x is cosine theta and y is sine theta, now we can express cotangent in terms of cosine and sine. So cotangent theta is equal to cosine theta over sine theta. Now, if you know one of the quotient identities, you know the other. If you know tangent, for example, say you have this one memorized, cotangent should just be the reciprocal of tangent, right? So we've got that relationship there. We also know the equation for this unit circle is x squared plus y squared equals 1, right? That's a circle with a center of 0 and a radius of 1. And again, we can make some more substitutions because x is cosine. So we could say instead of x squared, we could say cosine theta squared. Instead of y squared, we could say sine theta squared equals 1. Now, here's some notation that you need to get familiar with. We don't normally write cosine squared like this. We normally put that notation here, cosine squared theta plus sine squared theta equals 1. That's to show that the squared is not on the angle. The squared is on the function itself. The angle is still inside of the function. All right, this is called the Pythagorean identity because it's like a squared plus b squared equals c squared. So before we manipulate that, let's add this to our Pythagorean identity. Now, these often get rearranged. I wrote this as cosine squared plus sine squared equals 1. You could see it in that order, but you'll most often see it as sine squared theta plus cosine squared theta. So I'm not sure why the order is reversed when we sort of learn about this, but these are equivalent. So that's our first Pythagorean identity. And there are two others. Let's manipulate that equation a little bit to get two other Pythagorean identities that are common. So let's write this equation here. So sine squared theta plus cosine squared theta equals 1. So this is an equation, right? That means that I can perform some algebra on it, as long as it's all legal algebra, and I can manipulate the equation a little bit. So the first thing I would like to do is divide everything by cosine squared. As long as you do that to every term on both sides of the equation, that's all legal math, right? Okay, now what about sine squared over cosine squared? So just like we wrote, scroll back up, just like I wrote cosine squared before as cosine in parentheses squared, sine squared over cosine squared, that's the same as sine theta over cosine theta squared. And remember, our quotient identity says, okay, well, that's tangent squared. Sine over cosine is tangent. Tangent squared can be written like that. What's cosine squared divided by cosine squared? Well, that's just 1. And what's 1 over cosine squared? So that's like 1 over cosine, the quantity, squared. We know 1 over cosine is secant. So this is the same as secant squared theta. So that's our next identity. Our second Pythagorean identity is tangent squared theta plus 1 equals secant squared theta. All right, but again, if you remember the first one, and you know that the trick to get the other ones are, for our first one, divide by cosine squared, you can always figure out what this one is if you forget it. I would suggest memorizing it, but these can be derived. Let's go back to sine squared theta plus cosine squared theta equals 1, our original Pythagorean identity. Instead of dividing everything by cosine squared, let's divide everything by sine squared and see what that gets us. Again, you're allowed to do that because you're performing the same operation to every term on both sides of the equation, and it's multiplication or division. Sine squared divided by sine squared is 1. Cosine squared over sine squared, remember that'll be like cosine over sine cotangent squared, equals 1 over sine squared. 1 over sine is cosecant, so cosecant squared theta. And now when I write this down, I try to keep these last two in the same order because, again, I want to memorize them, and this is how I have them memorized. So I'm going to write cotangent squared plus 1 equals cosecant squared. Because these two, the way that you read them out is very similar. You just put a co in front of everything, right? So this one's tangent squared plus 1 equals secant squared. This one's cotangent squared plus 1 equals cosecant squared. So if you can remember that they're the same with co's in front of it as you read it out, that's another way to remember. All right, so part of your job is to memorize the reciprocal identities, which you kind of hopefully already have memorized. Memorize quotient and Pythagorean. And we want to use these to verify that the following equation is correct. So when we're told to verify something, because we're trying to show that this equation is correct, we can't use equation properties on this expression. So you can't treat the equation as true, meaning you can't say, I'm going to multiply secant squared to the other side. You have to work on one side only. So pick the side that has more stuff to do. Like this is the more complicated side. And what can I do to work on this? So there are a lot of ways to tackle these problems, and there's not usually just one correct path, but think of these as puzzles. You're trying to simplify this side to show how it can become sine squared. All right, so let's look at the fact that we can often rearrange these Pythagorean identities. I see secant squared theta minus 1. I do have a Pythagorean identity that involves secant squared and 1. If I were to subtract 1, so that this is secant squared theta minus 1, I would be left with just tangent squared on the other side. So one way to do this problem is to say, if I'm going to work on the left side, we usually just put an equals here. So I could say, okay, instead of secant squared theta minus 1, that can be substituted with a tangent squared theta, because tangent squared is equal to secant squared minus 1. it's still divided by secant squared theta. And so I'm one step closer to showing sine squared, but not quite. All right, so what's the next step? Another thing you can do is say, well, I have a lot of properties that change tangents into sines and cosines. They change some reciprocal functions into sines or cosines. So another good trick is so far we have used rearranged Pythagorean identities. It's also a good idea to write everything in terms of sine and cosine. What I mean by that is tangent squared theta can be sine squared theta over cosine squared theta. Instead of dividing by secant squared, I can say secant squared is 1 over cosine squared, right? So I can say times cosine squared theta over 1. So instead of dividing by secant squared, it's like saying you're going to divide by 1 over cosine squared, so let's just multiply by that reciprocal. All right, now what kind of stuff cancels? We have rational expressions here. Cosine squareds are allowed to cancel because this is multiplication, and you're left with sine squared theta divided by 1, so sine squared theta. As soon as you get the left side of the equation to match the right side, we usually indicate that we're finished with like a little box here. Now, there is another way to work on this problem, so I want to show you two common methods because they're both kind of useful. Let's go back and write the original equation. Secant squared theta minus 1 over secant squared theta equals sine squared. So another way to tackle this is anytime I see a binomial divided by a monomial, two terms divided by one term, I think, okay, I can divide each term by secant squared. We sort of informally have called this the heart method before. It's been a long time since we did rational expressions, but this looks like a heart, like you're allowed to do this. Secant squared divided by secant squared is 1. 1 over secant squared theta we can simplify. Make sure as you're doing these, by the way, that you put the thetas in. I know it's can get a little bit tedious, but none of these mean anything if you don't actually put the angle in. That's like doing math and putting a bunch of square roots without having any numbers in them. Like that doesn't make any sense. You have to have something in the function to make things work. Okay, anyway, what is 1 over secant squared? Cosine squared. Now here's a really common expression. The most rearranged Pythagorean identity is this original one. So if I were to solve this sine squared plus cosine squared for either one of those two trig functions, it could be that sine squared theta is equal to 1 minus cosine squared theta, if I subtract that over. Or if I solve for cosine squared theta, that's equal to 1 minus sine squared theta. Now, I have 1 minus cosine squared theta, so that's a rearranged Pythagorean. That's equal to sine squared theta. Heart method can be really efficient and nice. This one took a little more work because I used an identity, but then I had to rewrite sines and cosines. I had to flip stuff around. So kind of practice doing both as we're doing these. Let's take a look at another one. Tangent squared theta plus 1 times cosine squared theta minus 1. So this is definitely the more complicated side. We don't usually want to FOIL trig together unless it looks like it's going to FOIL nicely, but like tangent squared times cosine squared does not look fun. Always check for identities first. So let me go back to my Pythagoreans. Tangent squared plus 1 is secant squared. So we can simplify that. Cosine squared minus 1. Now be careful with this. 1 minus cosine squared is sine squared. If the subtraction is in a different order, that's equal to negative sine squared. Negative sine squared would be distribute a negative through that, and you get cosine squared minus 1. So this is negative sine squared theta. We are trying to show that this is equal to negative tangent squared theta. Another rule, by the way, you can't work on both sides at the same time and get them to meet in the middle, because that's still using equation properties to show that the two sides are the same. So you need to work on one side until you get the other side. Usually after I've used some identities, I rewrite in terms of sine and cosine. So secant squared is 1 over cosine squared theta times negative sine squared theta. You're multiplying two fractions together. You can merge them together. Negative sine squared theta over cosine squared theta. And remember, we're trying to get negative tangent squared. We have the negative. Tangent is sine over cosine. So this is negative tangent squared theta. These are called trig proofs. So you're trying to verify that one side equals the other. And you do have to show steps. Don't just jump from this first line to the final line. You're sort of proving to somebody step by step why this works. All right, what about number 3? So on this one, I don't know which side is more complicated. I usually consider the side with addition or subtraction to be more complicated, or there's more for me to do on this side than on this side. So I would say it's a good idea to start on the left again. Cosecant x minus sine x. That's not any of our identities, first off. There's no cosecant minus sine anywhere. So the next thing to do is rewrite anything that's not a sine or a cosine in terms of sine and cosine. So cosecant x is 1 over sine x minus sine x. If I'm trying to subtract a fraction and another number, I should get a common denominator. So if I put this whole thing over sine x, the first fraction already had the denominator. The second fraction gets multiplied by sine x over sine x to get that common denominator. So that becomes sine squared x on top. 1 minus sine squared x, back to your Pythagorean identities. That is cosine squared. The more that you practice these, the more you'll recognize that pretty quickly, by the way, over sine x. And even though you can't work on the side, it's okay to think about what the side would be. So like cotangent is cosine over sine, right? So do I have this? Do I have cosine times cosine over sine? Well, I have cosine squared. That is cosine x times cosine x over sine x. This cosine x divided by sine x can become cotangent x. And that would leave me with this cosine x still being multiplied. And that's what I was trying to get. I technically should write the answer to match exactly like this. So I'm going to do that. So, okay, fine. I left this cosine x here, and this cosine over sine is cotangent. I don't think that they're going to be that picky about things for the AP exam, but technically, if you're trying to prove something is true, there would have been one last little commutative property for me to make if I left my answer like that. All right, last example, and then we'll look at some rules. This one can be done two ways. I want to show both because both sort of scenarios get you stuck at some point. So let's go with the rule that I just said. There's some addition on the left side, so let's start on the addition side. Secant plus tangent is not anything. Those are not squared. There's no Pythagorean identity. So let's just begin by rewriting in terms of sine and cosine. Secant is 1 over cosine x. Tangent is sine x over cosine x. We're trying to get here. These do have a common denominator, so we don't have to make any adjustments, but we can merge it together to be 1 plus sine x all over cosine x. And then you kind of get stuck because 1 plus sine x is not any identity that we have. And I don't have anything I can work on. I don't want to turn around and divide because that's what I just did. So there's this trick where if you get stuck like this and there's nothing else to do, if you have a binomial, multiply by the conjugate. A conjugate we've talked about in the past is when you have a binomial and the only difference is the addition or subtraction sign in the middle. The conjugate of a plus b is a minus b, for example. Multiplying by the conjugate in the top and the bottom is legal because this is just, all I did here was multiply by 1. It's just a very fancy version of 1 that's going to help me. So you're allowed to multiply an expression by 1. When you multiply conjugates together, they multiply together nicely. 1 plus sine times 1 minus sine is 1 minus sine squared x. And in the denominator, I would not distribute this. I would just leave this as cosine x times 1 minus sine x. We did something like this with difference quotients too, by the way. We multiplied by conjugates, and the rule was multiply in the numerator and not in the denominator. And why is this helpful? 1 minus sine squared x will start jumping out at you the more you do these. This is the rearranged Pythagorean identity. It's equal to cosine squared x. And then the reason I did not multiply this cosine x through the parentheses is because I want to show myself that this cosine can cancel with one of the cosines in this cosine squared. And that leaves you with cosine x on top and just 1 minus sine x on the bottom. And remember, that's what we were trying to get to. All right, so for this one, I had rewrote in terms of sine and cosine, got stuck, multiplied by a conjugate. What if I begin on the other side? So what if I begin on this cosine x over 1 minus sine x side, and I'm trying to get secant x plus tangent x? Now, first of all, you are not allowed, this is illegal, you're not allowed to divide, you're not allowed to split this fraction up like this. We call this the reverse heart method. This looks like an upside down heart. You cannot do that. I did that all over my first calculus test in college, and I did not get a very good score. Okay, so what can we do? We're stuck to begin with, so we use that conjugate trick right away. The conjugate of 1 minus sine x is 1 plus sine x. All right, what do you multiply together? You multiply the conjugates together, 1 minus sine squared x. And you don't distribute, but you do show that cosine x is multiplied by 1 plus sine x. So in both scenarios, it's not about the top of the fraction or the bottom. It's about multiplying the conjugates and not actually distributing the other two. And then we kind of have the same math going on. So cosine x times 1 plus sine x over 1 minus sine squared is cosine squared x. Just like I did in this problem, I can cancel this cosine with one of the cosines in the bottom. Now I'm at 1 plus sine x over cosine x. Remember to look at the other side. What are you trying to get to? You're trying to get to secant plus tangent. Remember, secant plus tangent is 1 over cosine plus sine over cosine. So all you have to do is split this fraction up. I'm allowed to divide those, Hart method, right? I'm allowed to divide each term by a monomial. So this is 1 over cosine x plus sine x over cosine x, and that is secant x plus tangent x. So when I say you're not allowed to work on both sides to make them meet in the middle, you're allowed to work on this side and think about it, but you still have to end this side at exactly this side. I couldn't have stopped right here and said this equals this. I need to take it that one step further. So when you are verifying identities, there are many paths. I just showed some examples of like 2 ways to tackle these problems. Some ways are more efficient than others. So when you're doing homework, you might check your my answer key and see that I did something in 4 steps and you did it in like 10 steps. So it's just a matter of practice and sort of remembering some of these tricks. We're going to see a lot of the same types of setups a lot. Be on the lookout for rearranged Pythagorean identities. Always look for those to begin with. If you're not sure where to start, try making substitutions. Get everything in terms of sine and cosine. Look for things to cancel. Set up common denominators so you can start on the adding or subtracting side. And if a fraction is in terms of sine and cosine and there's nothing else that you can do, try this conjugate trick because you're really just multiplying by 1. It's just a very special version of 1 that's going to actually help you get somewhere. Okay, these take practice. I do think that they're kind of like puzzles. They can be kind of fun once you get the hang of it. So practice, practice, practice. Come into office hours if you need help.